Okay, so this is going to be the last video in chapter 14, and this time we're looking at heat transfer via radiation. So there's a bunch of examples on that. So this first one's not too bad. It says an athlete is sitting, I guess, naked in a locker room whose dark walls are pretty cool at a 15 degrees Celsius level. And it says it wants us to estimate the rate of heat loss by radiation. And his skin is, of course, higher than that. It's at 34 degrees. So the key, I think, in a lot of the problems in this section is you're looking at rates of change. So a rate of change, if you haven't had calculus, you just think of it as a slope, right? So this is what we're looking at over here. The change in heat over the change in time. That's going to give us like heat loss or gain. And since this time the athlete's higher than the walls, those walls are going to kind of try to suck some heat through the air, or through the air between them. I guess where heat transfer, when you think radiation, you really have to have a medium, but they're going to kind of try to pull heat away from the athlete. But anyway, it's a rate of change. So in calculus, this would be a derivative. So you would be thinking about it in terms of a derivative if you hadn't had calculus. Think of it as a slope, okay? It's just a slope. All right, so that's the equation. I think the only thing we need to be careful about is for these problems in this section, you need to make sure you're in SI units. Some of the problems we did before had Celsius, and we left them in Celsius when we were working with specific heat. These are going to convert to kelvins, which is the SI unit for temperature. So 34 plus 273, what's that going to be? 307 kelvins. And 15 is going to be 288 kelvins. Okay, so for this circumstance, we're going to say the emissivity constant is 0.7. Remember, that just governs like how shiny the materials involved are. The walls are dark, so it kind of makes sense that it's high. Remember, emissivity constants are high if they're like very black. So anyway, the Stefan Boltzmann constant is just a constant, so we're going to put that in. 5.67, it's a small constant, times 10 to the negative eighth. I'm not going to put all the units in there, it's just going to get confusing. And then we need some kind of surface area involved, so how much surface area of this athlete's skin is there, and the problem says that it's about 1.5 meters squared. That kind of makes sense. I think that's a reasonable number. Anyway, so there's that, and then we're going to look at the temperature differential. So I'm going to start out with a bigger one, just like some of the other problems here in this chapter. You kind of like want to probably pick the bigger one minus the smaller one, just so you get the temperature change. That's how I decided. I mean, it's nothing big. You could do it the other way and then just take the absolute value of your answer at the end. So, and because it would be negative then, of course. But anyway, so you plug those numbers in your calculator, do some significant figures, and you get 120. You could keep track of, like I said, all the, these are degrees Kelvin, this is meters squared, this has some kind of funky unit, and so does emissivity is unitless, excuse me. But basically, remember, let's think about what this is. This represents a rate of heat over a rate of time. So that's like change in heat over time. What is heat, though? We said heat is energy. So this is like energy over time. What's energy over time? Energy over time is power. So this is watts. Okay? So that's about what's happening. It's decreasing by about 120 watts. And it says in the book, the output of this resting person is a bit more than what a 120 watt light bulb uses. So it's a decent amount of power. Okay, or a decent amount of rate of heat being lost over time. Okay, let's look at another example. So that one wasn't bad. The next one says you've got two teapots, a ceramic teapot and a shiny teapot. So we've got two different emissivity values. And we're just going to say they're about the same size, and we're just going to estimate their area. So you might have that in several of your problems this time. So remember, you just might want to have to estimate the area. So we're going to say that the area of this teapot is like about 0.1 meter. So 10 centimeters on a side, that seems reasonable, right? And we're just going to pretend it's a cube. So if we do that, what do we get? The area. Remember, this isn't volume. We don't want the volume, so it's not 0.1 cubed. It's like how many surfaces are exposed to the edges. So the top edge that's exposed to the air doesn't count. So how many faces does the cube have? It has 6. But we're going to say this top edge up here, this guy is not really on touching the edges of the teapot, so it doesn't count, because we are wanting to figure out the rate of heat loss by each teapot, not by the tea touching the air. Okay? So let's say that that's 5, and then each one of those faces is 0.1 squared. So what is that? 5 times 10 to the negative second, if you put it in your calculator, meters squared. Okay? So that's something you might have to do, is estimate on a couple of your problems, I think. So, like I said, part A said estimate the rate of heat loss from each, just like we did in the previous one. So we're using that same formulation that Stefan and Boltzmann came up with. So let's see. We're going to do it for each one separately. So for the first one, well, maybe we'll just try to do them together. Let's see. So emissivity, we'll just leave then, I guess. We'll put in the constant, 5.67 times 10 to the negative 8th. Put in the area we got, 5 times 10 to the negative second. And then the temperature difference. What are these teapots doing? It says they're both at 95 degrees Celsius, so pretty hot. That tea is hot. And it says the surroundings are at 20 degrees. So we're going to say 95 degrees is 368 kelvins. So we'll do that to the 4th power minus the surrounding air temperature, 273, plus 20 is 293. Oh, I had it up here. Oh, to the 4th power, right? That's a 4th superscript right there. Okay, so let's see. So we just left E unknown, so we could do them both at the same time. So that all works out to about, if you use your significant figures, the book says about 30 watts. Let's see exactly what it does in my calculator. So I'm gonna do it in my calculator. Let's see, 5.67 times 10 to the negative 8th. Times 5 times 10 to the negative second times 368 to the 4th minus 293 to the 4th. Yeah, I got about 31.098. So if we think about significant figures, we don't have more than one, really, do we? Yeah, I think we only have one significant figure. So I'm going to say that's about 30 with the book. That's right. Remember, emissivity is unitless. So since it's a change in heat or a change in energy over time, it's a power. So we put watts. So then we said the ceramic pot is probably pretty black, so it's got an emissivity or a shininess constant of 0.7. So you do 0.7 times 30, and what do you get? Remember, we're only doing one significant figure here, so it says 21. So we'll say for the ceramic teapot, its power or heat loss is 20 watts, and for the shiny teapot, that means it's real shiny. It's not going to do too much. It's not going to be losing too much heat or anything because of this. It's crazy that shininess affects it that much. What's 0.1 times 30? 3? Yeah. So that's 3 watts. Okay, part B of this question said estimate the temperature drop after 30 minutes for each. So we're supposed to figure out how much the temperature drops after 30 minutes. And it looks like I need a bigger, I need to scroll on this guy. Let's see, hold on just a sec. Whoa, that's not enough. Well, I guess we'll just leave it for now. But all right, so we want to figure out the temperature drop after 30 minutes. So here's how we're going to do that. We're going to first think about what we had for a change in heat based on specific heat and temperature differential from before. And remember, the mass also mattered. So if we want to look at um, estimating the temperature drop after 30 minutes, we could just like say apply a change in time of 30 minutes. So we're just going to put change in time on both sides of this equation. So we're like dividing by change in time on both sides. And then we're going to solve. Remember they said estimate the temperature drop after 30 minutes. Remember, what are we solving for? If we want the temperature drop, we're solving for delta T. Okay? So we need to solve for delta T eventually. So you can see what I did here is I just took delta temperature over delta time, and I divided that MC to the other side. So that's why it's divided by MC here. Okay, let me clean that up now a little bit. So we're just solving for change in temperature over change in time, and then we'll plug in what we know. So we said this was from right up here, right? So we've got E times 30 watts, depending on which one of these teapots it is, over the mass of the teapot. I think they also told us that. Is it listed up here? Ah, yes. The mass of the teapot is 75 kilograms, so that's not bad. And then we say C. Remember, C is the specific heat. So the specific heat of our teapot is, well, let's just think that most of the stuff inside there is water, so we'll just use water's specific heat. So we'll go 4.186 times 10 to the third joules. Oh, I don't want to put all my units in there for specific heat. Ah, it's just going to get ugly. Okay. So now we've got that. So that'll give us change in temperature over change in time. That'll give us how fast the temperature is dropping. But we want to know specifically 30 minutes later. So let's just grind those numbers down. And we'll see what we get. So that's going to be, I think, E times about 0.01. So that's what change in temperature over change in time is. So I'm just going to multiply that change in time up here. And they asked us about 30 minutes. So what is that? So we'll get E times 0.01 times 30 minutes. How many seconds is that? That's going to be 30 times 60. Yeah. So 1800 seconds. So 1800 seconds later, we're going to have 18 E and then we just plug in the different E's for the two pots. So the ceramic pot, 1800 seconds later, it's going to be, let me zoom out a little bit. So the ceramic pot, 18 seconds later, is going to, well, let's put this in here. So 18E. So for the ceramic pot, we're going to go 0.7. So that's going to give us about 12 degrees Celsius. And for the shiny pot, it's not going to lose. It's going to be about 2 degrees Celsius. So notice that the shiny pot has a big advantage because it didn't lose nearly so much temperature. So remember, these represent how much temperature has been lost, and that shiny pot did a lot better there. Okay. All right. So you might want to look in the book if you want on the units here. So this was like watts. Should I just put those in? Let's go back and put those in and see if this makes sense. It's probably good. So this was watts, right? From up here, watts are joules per second. Mass is kilograms. Oh my gosh, it's going to be hard to fit this in here. Let's see. So we've got that. And then this value of the specific heat, if you remember, you can go back and look at the beginning of the chapter, but it's joules divided by kilograms degrees Celsius. So that's why we got our degrees Celsius here at the end. So let's make sure, let's just look at the units there. So we've got joules over seconds over kilograms, joules over kilograms, and degrees Celsius. So if we flip that up, then what happens? What do we get? So we get that these kilograms cancel out, right? And then it's like joules over seconds over joules over degrees. So the two joules cancel out, and you get seconds, and that degrees is going to flip up on top. And then right here, when we put the delta T, that's going to give us seconds, and you can see that those will cancel. And you get degrees Celsius. So that's why it's in degrees Celsius, even though up at the beginning in the delta Q over delta T, the original formulation, we had changed it into kelvins. So that's a little bit weird, but anyway. Let's look at another example. Zoom back in a little bit. Okay. So the third example is someone getting a tan. So it says, what is the rate of energy absorption from the sun by a person lying on the beach on a clear day? And the sun's supposed to make a 30-degree angle with the vertical. Assume the emissivity of this person is 0.7, so they're not a very shiny person. And remember, the sun has this special 1,000 number in front. So remember, the sun has that special 1,000 in front because it says on a clear day about 1,000 watts per meter squared reach the Earth's surface. So that's kind of like the power output of the sun, if you will. On a clear day, at least. It's only approximate. So yeah, I think we're just going to plug in numbers on this one. So we're going to put our 1,000 in there. We said the emissivity of this person is about 0.7. The area exposed to the sun, so we do a kind of little estimation. Person usually about 6 feet, so that's like 2 meters and about that wide. So I hope you love my little diagram. So for the area, we're going to go 2 times 0.4 or 0.8, and the cosine, we said that I should say the sun makes a 30-degree angle during this season of the year. So we do that. What is the cosine of 30 degrees? Do our little trig triangle. We might do that without a calculator. It's going to be 1 root 3 over 2. So it's going to be root 3 over 2, which if you put it in your calculator will give you 0.866. This is 0.8. 1,000 times 0.7 is 700. And I guess I'll leave the calculator to do the rest. So that's about 500 watts. So that's how much energy this person is absorbing. Kind of scary. So it says if the person wears light-colored clothing, E is much smaller, so the energy absorbed is a lot less. And we've all experienced that. If you wear a dark shirt, it's going to absorb way more energy, and you're going to get hotter way faster. You're going to, because of that absorbed heat or absorbed energy. Okay, let's look at this last one. I think this one's the only one that's a little bit strange, so we might need a little bit of help on this one. Those are all pretty straightforward. It's a neat problem, though. It says star radius, so we're going to try to estimate the radius of a star besides our own. It says the giant star Betelgeuse emits radiant energy at a rate 10 to the 4th times greater than our sun. So it emits energy at a rate 10 to the 4th bigger than our sun. Okay, they give us a bunch of other information. It says that star Betelgeuse, its surface area, or its surface temperature, excuse me, is only half that of our sun, so it's only 2,900 kelvins. Our sun's double that. So its surface temperature is only half the temperature of our sun. And let's see, what else? I think it told us the radius of our sun. Yeah, so I put that in there, and it said emissivity is approximately 1 for our sun or Betelgeuse. Yeah, they absorb and emit energy at a pretty gigantic rate. So pretty much perfect, so we'll use 1. All right, so we're supposed to figure out the radius. Well, first, I think the key that they gave, the key thing to this problem is that they told us it's energy emission, not amount, but it's energy emission rate. Just like in calculus, there's all kinds of rate problems. So this is almost like a related rate problem from calculus, except they've given us all the stuff. We don't have to find it. So we know about how heat changes with respect to time, so we know about rates. So that's what tells us that this is like a rate problem. So we go back, we look at that Stefan-Boltzmann rate heat equation, and we put that down. Okay, so since we're trying to find radius, you might think, well, what involves radius here? Well, the area involves radius. You might solve for radius. So that means that A equals delta Q over delta T, all divided by the emissivity, that constant, and T to the 4th power, right? If you're solving for A. Then you say, okay, well, what's specifically happening here? Well, we have a sphere. Well, that's really bad. Hard to draw a circle with this, apparently. So let's go for the sun. I guess the sun is yellow. Holy moly. Well, imagine that that's a sun, like Betelgeuse, or our sun. And it's a sphere. So if you remember, the area on the surface of a sphere is represented by 4 pi r squared. That's the surface area of a sphere. So that's what we did here. And then we finally got our r that we're looking for. Okay? So 4 pi r squared is this stuff. So I'm going to put quotes, that same stuff. So then what we're going to do is we're going to form a ratio. Since we know the radius of our sun, and we want to know the radius of Betelgeuse, we could do a ratio of what's happening with our sun to what's happening with Betelgeuse. And basically just do this twice. One for Betelgeuse, one for our sun, and then divide, and hopefully that ratio will be able to give us what we're looking for, the radius of Betelgeuse. Okay? So it looks ugly, but I don't think it's too bad. So the book didn't say any of that. Anyway, if you form that ratio, we said the emissivity for both stars is going to be about the same. Stefan-Boltzmann constant is constant, so those both are going to cancel out, right? The 4 pi's are going to cancel out in both cases. So let's kind of see what's left here. So if we do that, what's going to be left? We're going to have the radius of Betelgeuse squared over the radius of our sun squared equals, and then we've got the way that heat is being emitted by Betelgeuse, the way that heat is being emitted by our sun, and basically these are just the temperatures as well. So what's going to be left is, well, let's just, I guess we'll write it down. The heat emission rate of Betelgeuse divided by the heat emission rate of our sun. And these are both on the bottom, so since they're like that, I'm going to just flip them. Does that make sense? Like this guy's going to go up there, and this guy's going to go down there. We can flip them and do a little reciprocal. So temperature of the sun to the 4th is now on top, and temperature of Betelgeuse to the 4th is now on bottom. And then we say, okay, do we know those things? I think we did. So they said that, remember at the beginning, the emission rate of our sun was 10 to the 4th times bigger. Or excuse me, the emission rate of Betelgeuse, if you look at the problem, was 10 to the 4th times more than our sun. So since Betelgeuse is on the top and our sun is on the bottom, that means that number is going to be 10 to the 4th. We don't even need to know the specific numbers. That gave us basically a ratio, okay? So then we also knew, remember, that the temperature, or the surface temperature on Betelgeuse was only half the temperature on our sun. So I wrote that right here. And we've got sun over Betelgeuse like that. So I'm going to solve that so where it's sun over Betelgeuse. So I'm going to go divide Betelgeuse over here and multiply by 2 over there. Let those 2's cancel. So I get 2 equals, ooh, it's pretty ugly. Let's do a different color. So I get 2 equals, so I divided by Betelgeuse on both sides, right? Very easy. But 2 equals the temperature of the sun over the temperature of Betelgeuse, which is what we have right here, except it's to the 4th power. Can't you go like this? Scribble that out and just say it's 1 to the 4th power. Yes, you can. So that's just 2 to the 4th power, and that's what we've got. So we've got the radius of Betelgeuse squared over the radius of the sun squared equals this number, right? So let's figure out what that number is. It's 16 times 10 to the 4th. Yeah. So that's what that number is. So we're going to put that right here, because remember that was what was equal to r sub b squared over r sub s squared. And just like I did with that spot, I mean, you do your algebra how you want to, but I'm basically going to now just think about this as it's all squared. So we can square root both sides. That's where this square root came from. And then multiply up the r sub s. The r sub s is going to go up there. And that's basically it. So we've got that square root, 16 times 10 to the 4th power, square root of that, times the radius of the sun. Oh, yep, we knew the radius of the sun was 7 times 10 to the 8th meters. Pretty big. And we now know the radius of Betelgeuse. So definitely only probably have one significant figure, but that's all we're looking for. So looks like this guy is a lot bigger. You're saying, well, 10 to the 8th versus 10 to the 11th, how much bigger is that? Well, it says if Betelgeuse were our sun, it would envelop us because the Earth is only 10 to the 11th meters away from the sun. So that would suck for us if Betelgeuse was at the center of our solar system. Anyway, hope you found this useful, and you can start the problems whenever you need to. Adios.